Alright, welcome to Unit 3, Lesson 7 on friction force. In this video we're going to be going over the second example problem along with the force of friction. And we're also going to go over a quick introduction over the two different types of friction that we're going to be dealing with. The two types are kinetic friction, which is the friction that occurs between a surface and a moving or a sliding object. And we're also going to talk about static friction, which is the force of friction between an object and a surface where the object isn't sliding or isn't sliding yet. There's going to be a fairly different value between these two coefficients. Now, for clarification, the surfaces can be the same material between the two. So say we had a wooden block and a concrete floor, the coefficient of static friction between that block and concrete floor is going to be a higher value than the coefficient of kinetic friction. And that's because objects that are sliding across typically have a value less than objects that are just sitting in place. If you look in your book, there's a little bit of a diagram demonstrating this. And it essentially shows the value of static friction slowly increasing until it hits that value of maximum static friction. That maximum static friction is sort of a threshold value. Once we hit that force, it means that we have enough force applied to the object to begin moving it, which we see a quick jump downwards. Once we are able to begin moving an object, we can slide it along the floor and then use the coefficient of kinetic friction. The coefficient of kinetic friction is typically less than that of the static one, meaning that essentially once we get an object moving, it's going to be easier to move than it would have been when we're just trying to get it going. Anybody who's really tried to drag any sort of heavy object, I always comes to mind the thought of a sled on snow. If you're trying to pull a sled on top of the snow, it can be quite difficult to get going if it's heavy. But once you get over that initial hump of moving it, it's easy to drag along the slope. There's a fairly large, from what I've noticed, difference between the coefficient of static friction and kinetic friction with, say, a wooden sled on snow. Alright, so that said, let us jump into this problem. This problem says that a 70 kilogram oak desk, which I've sketched out as a couple blocks here because there's parts A and B, is at rest on a level oak floor. Okay, so we have a desk on a wooden floor. And the coefficients here, coefficient of static friction I've put up here is 0.50. Coefficient of kinetic friction is 0.30. Our job is to determine the friction force if the applied force is a 200 newtons. So let me put the 200 newton applied force here. F1 is equal to 200 newtons. And later for part B, we're going to get to where the applied force is going to be 450 newtons. And we're going to see if we get some sort of difference here. Alright, well, first step of this problem, let's figure out our FG so we can figure out normal force, so we can figure out friction. I think that would be a wise choice. So, where to start? Let's just start changing our marker color. I've got red and blue out already. Well, we'll do red. Alright, well, first thing that I want to do is I want to find normal force. So, in the y direction here, we have force of gravity downward. We've got normal force upwards. And moving against our attempted motion, we've got some force of friction business happening. Okay. We want force normal because ultimately we want to be able to use this formula up here. Force of friction is equal to coefficient of friction times normal force. Okay, so we've got F net equals, well, we're going to say F net y is equal to mass times acceleration. But in the y direction, up and down, this object isn't jumping, it's sliding side to side. So there's no acceleration in the y direction at all in this problem. So that's going to make force net y equal to 0, because anything times 0 is 0. Alright. We can also say then in the y direction, F net y is equal to normal force plus force of gravity. Well, we can then make 0 equal to force normal plus our force of gravity, which is 70 kilos times negative 9.81 meters per second squared, leaving us with a normal force of I have it written down here somewhere, 686.7 newtons. 686.7 newtons. Alright, now that we have the normal force, let's plug it into the force of friction formula. Now, before we get too far, if you recall from that diagram that I talked about on the last page, there's that value of static friction. Now, if this block begins at rest, which we're probably assuming that it does, it means that there's a threshold value that we have to surpass. And that threshold value is going to be known as the maximum static friction value. And we have to do a little bit of a test. So I'm going to say we want to determine maximum static friction. So if we know how heavy this block is, we know how rough the surface is, we can determine how hard we have to pull this block to get it going. Alright, once it's going, it's going to be easy. Meaning that if we have enough to get it going, we're going to be able to get this thing going pretty quickly. Alright, so let's say we have this formula, force of friction is equal to coefficient of static friction times the normal force. So force of friction is equal to 0.5 times 686.7 newtons. Therefore, the force of friction here is equal to 343.35 newtons. This is max static friction. And what this value means is that in order to get this block sliding, we have to pull with a force at least 343.35 newtons. If we look at what we're pulling at, we're only pulling with 200 newtons, meaning that there's too much friction here to move this block. Right? This block has so much friction that even a force of 200 newtons can't get it to move. So, this value that we solve for, and I'm going to go ahead and say that this is probably a fairly common mistake, is that generally when people get this value, they're just going to go ahead and say, well, I've solved the force of friction here. The force of friction is 343.35 newtons. That's not correct, because this 200 newton value is not enough to get this block moving. But if we added a force of friction of 343 newtons to this side, the leftward side would have a greater force than the right side, meaning that force net here would come out to be negative, 143 newtons. Well, this block would be accelerating to the left. But friction doesn't speed anything up. Friction counteracts motion. So this block of static, or this value of static max friction, is more of a threshold value that we're trying to test against. So really, since this block doesn't move, we're going to say that this force of friction value right here is going to make, since it's not moving, it's going to make our F net x 0. Therefore, force of friction is going to equal 200 newtons. It's going to match that strength that we pull it with. All right? Because ultimately, we need, for this object not to move, an F net value in the x direction of 0. So there has to be, if there's 200 pulling this way, has to be 200 pulling that way. All right, I really digressed on that. Let me move on to part B. Okay, so now we have a 450 Newton force pulling on this thing. Let me sketch on the rest of the forces. Even though they're essentially the same, we have pulling up, we're going to have, whoops, that's the box tool on there, but it's fine. Still got force normal. Pulling down, we've still got force gravity. Pulling back, we still have force of friction. All right, but we have a little bit of a different situation here. We already know what the normal force is here. Right, our normal force is 686.7 newtons, and we actually already know our force of friction because it's going to be, the max static friction. It's the same as over here, except now this value that we're pulling with, force 1, well, force 1 is greater than max static friction. Right, greater than max static friction. That's very important because now our block can surpass this threshold. If we could say that pulling 450 newtons is stronger than this, means it's going to start to move or accelerate to the right. Well, once this block begins sliding, the force of friction decreases. And we're actually going to use the coefficient of kinetic friction, which is 0.3, meaning that there's going to be even less friction in part B than there was in 1, simply because we pulled it hard enough to make it start moving. All right, so I'm going to say here that because of this, therefore, our block will accelerate. Block will accelerate, and we use the coefficient of kinetic friction. All right, well, let's do the math on that then. Figure out this coefficient of kinetic friction. Let us do force of friction is equal to now the coefficient of kinetic friction times the normal force. And that leads us to force of friction, which is 0.3 times, what was the normal force up here? 686.7. And when we plug that into our calculator, we get a value of 206 newtons. All right, and there you have it. So here you see that any value really of applied force up to 343 newtons will give us a force of friction that essentially matches what we have on the applied force side. So if we had a force of even 300 newtons pulling on this, we would then have a force of friction of 300 newtons. Now when we come down to B, we have a force of 450 newtons, which is strong enough to make this thing begin moving, and we can now use that coefficient of kinetic friction. All right, I think that's a pretty good wrap, and the end of example 2.